Hey guys, I'm Robert and I'm going to show you guys how to do stoichiometry. Despite its intricate name, stoichiometry is a simple tool that uses a balanced chemical equation and it shows the relationship of moles of one substance to moles of another. For example, 4 moles of iron for every 3 moles of oxygen, 4 moles of iron for every 2 moles of Fe2O3, and 3 moles of oxygen for every 2 moles of Fe2O3. In this video, I'm going to go over 5 stoichiometry problems. Let's begin. If 3.6 moles of iron react with excess oxygen, how many moles of Fe2O3 can be produced? We're given 3.6 moles of iron and we're trying to figure out how many moles of Fe2O3 can be produced. Our main objective is to convert the moles of iron to moles of Fe2O3. We need to make a mole ratio of the Fe2O3 and the iron using this equation. And for this equation, there is 2 moles of Fe2O3 required for every 4 moles of iron. This is our mole ratio. It's also known as a stoichiometric factor, and it shows that there is 2 moles of Fe2O3 required for every 4 moles of iron. It works just like converting between grams and moles. The moles of iron will cancel out, leaving us with moles of Fe2O3, and you just need to take the 3.6, multiply times 2, then divide by 4. I got 1.8. So 1.8 moles of Fe2O3 is produced. What mass of oxygen is consumed from the complete combustion of 0.2 moles of propane? We're given 0.2 moles of propane and we're trying to figure out what mass of oxygen is required. First thing we need to do is convert the moles of propane to moles of oxygen. We need to make a mole ratio of the oxygen and propane using this equation. For this equation, there is 5 moles of oxygen required for every mole of propane. This is our mole ratio. It's also known as a stoichiometric factor, and it shows that there is 5 moles of oxygen required for every 1 mole of propane. It works just like converting between grams and moles. The moles of propane will cancel out, leaving us with moles of oxygen, and you just need to take the 0.2 and multiply times 5. We got 1 mole of oxygen. The last thing we need to do is convert the moles of oxygen to grams of oxygen. There is 32 grams in 1 mole of oxygen, and the moles of oxygen will cancel out, and you just take the 1 and multiply times 32. So 32 grams of oxygen gas is required. What mass of hydrogen gas is produced from the reaction of 0.87 grams of aluminum with excess hydrochloric acid? We're given 0.87 grams of aluminum, and we're trying to figure out how many grams of hydrogen gas is produced. First thing we need to do is convert the grams of aluminum to moles of aluminum. There is 27 grams in 1 mole of aluminum. The grams of aluminum will cancel out, leaving you with moles of aluminum, and you just need to take the 0.87 and divide it by 27. I got 0.0322. Next thing you need to do is convert the moles of aluminum to moles of hydrogen, and we need to make a mole ratio of the hydrogen and aluminum using this equation. And for this equation, there is 3 moles of hydrogen required for every 2 moles of aluminum. This is our mole ratio. It's also known as a stoichiometric factor, and it shows that there is 3 moles of hydrogen required for every 2 moles of aluminum. It works just like converting between grams and moles. The moles of aluminum will cancel out, leaving you with moles of hydrogen, and you just need to take the 0.0322, multiply times 3, then divide by 2. I got 0.0483. The last thing you need to do is convert the moles of hydrogen to grams of hydrogen. There is 2.016 grams in 1 mole of hydrogen. The moles of hydrogen will cancel out, leaving you with grams of hydrogen, and you just need to take the 0.0483 and multiply times 2.016. And I'm going to stop at 3 decimal places, so 0.097. 0.097 grams of hydrogen gas is produced. What mass of chlorine gas is required to react with 1.65 grams of P4? We're given 1.65 grams of P4, and we're trying to figure out how many grams of chlorine gas is required. First thing we need to do is convert the grams of P4 to moles of P4. There is 124 grams in 1 mole of P4. The grams of P4 will cancel out, leaving you with moles of P4, and you just need to take the 1.65 and divide by 124. I'm going to stop at 0.0133. Next, we need to convert the moles of P4 to moles of chlorine using this equation. And for this equation, there is 6 moles of chlorine required for every mole of P4. This is the mole ratio. It's also known as the stoichiometric factor, and there is 6 moles of chlorine required for every mole of P4. It works just like converting between grams and moles. The moles of P4 will cancel out, leaving you with moles of chlorine, and you just need to take the 0.0133 and multiply it times 6. I got 0.0798. The last thing we need to do is convert the moles of chlorine to grams of chlorine. There is 70.9 grams in 1 mole of chlorine. The moles of chlorine will cancel out, and you just need to take the 0.0798 and multiply times 70.9. Stop at 2 decimal places, so 5.66. So 5.66 grams of chlorine gas is required. 1 mass of oxygen gas is required for the complete reaction of 55 grams of glucose. What masses of CO2 and water are produced? This one is a 3-part question. We have 55 grams of glucose. We're trying to figure out how many grams of oxygen is required and how many grams of CO2 and water is produced. Since we're given 55 grams of glucose and we're trying to find all of these, we can solve for any one of them first. First, I'm going to solve for how many grams of oxygen is required, but first I need to convert the grams of glucose to moles of glucose. There is 180.2 grams in 1 mole of glucose. The grams of glucose will cancel out, leaving us with moles of glucose, and you just need to take the 55 and divide it by 180.2. I'm going to stop at 3 decimal places, 0.305. Now we need to convert the moles of glucose to moles of oxygen, and for this equation, there is 6 moles of oxygen required for every mole of glucose. This is the stoichiometric factor. It shows that 6 moles of oxygen is required for every mole of glucose. The moles of glucose cancel out, leaving us with moles of oxygen, and we just need to take the 0.305 and multiply it times 6. I got 1.83. Last thing we need to do is convert the moles of oxygen to grams of oxygen. There is 32 grams and 1 mole of oxygen. The moles of oxygen will cancel out, leaving us with grams of oxygen, and you just need to take the 1.83 and multiply times 32. I'm going to stop at 1 decimal place, so 58.6. So 58.6 grams of oxygen gas is required. Now we need to figure out how many grams of carbon dioxide is produced. We know that we have 0.305 moles of glucose, so we need to convert this amount to moles of CO2. And for this equation, there is 6 moles of CO2 for every mole of glucose. This is our stoichiometric factor. It shows that 6 moles of CO2 is required for every mole of glucose. The moles of glucose will cancel out, leaving us with moles of CO2. But now we need to convert the moles of CO2 to grams of CO2, and I'm going to combine this in one step. There is 44.01 grams in 1 mole of CO2. The moles of CO2 cancel out, leaving us with grams of CO2. And at this point, you just need to take the 0.305, multiply times 6, then multiply times 44.01. And stop at 1 decimal place, so 80.5. So 80.5 grams of CO2 gas is produced. Now we want to figure out how many grams of water is produced. We know that we have 0.305 moles of glucose. We need to convert this amount to moles of water. And for this equation, there is 6 moles of water for every mole of glucose. The moles of glucose will cancel out, leaving us with moles of water. And I'm going to convert the moles of water to grams of water in one step. There is 18 grams and 1 mole of water. The moles of water will cancel out, and we just need to take the 0.305, multiply times 6, then multiply times 18. I got 32.9. So 32.9 grams of water is produced. Thank you guys so much for watching this video. I hope to help. Please hit the like and subscribe, and good luck.